right, here we go, folks. Introduction to quadratic functions. We're going to be learning a whole lot of stuff here, basic stuff, about our quadratic functions. So that includes what they are, their properties, max and mins, domain, range, vertex, axis of symmetry, and how to graph them very quickly. So let's get started. So to define a quadratic function, it's just a function of degree 2 that can be written in the form of f of x is equal to ax squared plus bx plus c, where a, b, and c are all going to be real numbers. That's what this symbol means. They're in the set of real numbers. And we're going to say that a is not equal to 0. And the reason that we do that is because if a is 0, this whole term goes away and it becomes a linear function. So in order for it to be quadratic, a has to be something other than 0. And if you were to graph it, it would be a parabola, which we have seen in the past. Okay, so this is the quadratic term, the ax squared. That's the linear term, the bx. And then c is considered the constant term. And we'll be referring to them by those names as we go along in this unit. So like I said, when you graph it, it's going to be a parabola. This is our very basic y equals x squared parabola. So let's talk about it. First of all, there's a vertex, which is going to be the highest or lowest point on the parabola, depending on which way it's oriented, if it's facing up or facing down. So for this one, I will put the vertex in here. This would be the vertex. It has a lowest point on the parabola, because technically these go on forever. I know on the computer there's no arrows, but there's arrows on each of these branches here going forever and ever to positive infinity. So this one would have a lowest point. And what's interesting is, hello, there we go. The axis of symmetry, which is a line that goes through the graph where if you fold along that line, all the points on one side of the graph would line up on the other side of the graph. Well, parabolas are all symmetric. So I can actually see how good I can do. Ooh, okay, not bad. Here's the line of symmetry, or axis of symmetry. When you draw it in, it should be dashed because it's not technically part of the parabola, the graph itself, but it is a property of it. And it's a vertical line that's always going to go through the vertex. So that means this vertex is really important because it's like that turning point here of our parabola from one side to the other side. If I were to fold this over across this line, all of these points would land on those points. And so if you look at this distance right here, from the axis of symmetry out to this point, it's going to be the same as the distance from the axis of symmetry to that point. And that's going to be very helpful when we go to graph these things. Okay, let's get rid of all my little drawings here. Moving on. Okay, so if you may recall that whenever we set our function equal to 0, what you're saying is the y values are 0. What are the x values? Well, those are the x-intercepts. It's where your graph crosses the x-axis. And if we don't know exactly what a, b, and c are, we could actually calculate out those x-intercepts using the quadratic formula. So in general, each of these x-intercepts are solutions to the quadratic formula. So here's one, and I know I've broken it up like this on purpose. Negative b over 2a minus this whole quantity, and then this is negative b over 2a plus this whole quantity. And so if we wanted to figure out where this vertex or axis of symmetry is in general, if it's not always centered at the origin, we know that the axis of symmetry is going to lie on this line that's halfway between any 2 points, right? So if I took these two x-intercepts, the average of them would be where the axis of symmetry is. So we're going to take the average of this big number and this big number, all in general terms. It's going to be lots of fun. Just watch. Okay. Yikes. Okay, so we add these two numbers and divide by 2. That's how you take the average of something, right? Now think about this. This is actually why I broke it up like this. This is a negative of this big quantity, and this is a positive of this big quantity. So when we add these together, they actually cancel each other out. So you end up getting just this plus this over 2. And when you combine this, they have the same denominator, so this is a negative 2b. So negative 2b over 2a all over 2. And when you simplify, it's really negative b over a times 1/2, because these cancel. Dividing by 2 is the same as multiplying by a half, and you get negative b over 2a, which, if you think about it logically, without having to do the algebra, it's right there, the negative b over 2a. And we knew this because if we took the average, these things would cancel out. It would just be that. Anyway, what this does is it allows us to figure out what the equation of the axis of symmetry is. X equals negative b over 2a. And remember, it's a vertical line, so it should be an equation of x equals some number anyway. So if we use this to find the x-coordinate of our vertex and the axis of symmetry, this can be very helpful. Remember that the vertex goes through the axis of symmetry, so they'll have the same number. So if we plug negative b over 2a into this function, we can get the y-coordinate of our vertex. We're going to come up with an actual formula to figure out the y-coordinate of our vertex. Yes, I know you could just, you get x equals 2, plug 2 in and calculate it out. But sometimes we don't want to actually figure out the x-coordinate. We just want the y-coordinate. So that's why this is going to be useful. So let's do it. Okay, so we plug in negative b over 2a into this function. And we simplify. So when you square this, you get b squared over 4a squared. We still had an a out there. So combining the b and the negative b, that gives us negative b squared. Okay. Leaving that c alone, I'm not actually going to combine it with these two, and you'll see why in a second. So I'm going to combine just these two together. That means I need to get an LCD. So for this one, I'm going to have to multiply the top and bottom by 2. So here it is. And now I can combine these. So b squared minus 2b squared is a negative b squared. So negative b squared over 4a plus c. And I'm just going to simplify this around, just reorder it, because why not? I hate starting something with a negative if I can possibly avoid it. So c minus b squared over 4a. That would be the y-coordinate of your vertex. Okay, so in conclusion, all of this boils down to this formula right here. This is how you calculate what your vertex is. Okay? Remember that. All right, next thing that we're going to take a look at. C. We have A, B, and C. What is the y-intercept? Well, there it is, right there, the y-intercept. It's just hanging out there ready for you to use it. So why is that the y-intercept? Well, if we're trying to figure out the y-intercept, it's where x is 0, right? So plug 0 in into your equation here, and this term goes away, and this term goes away, and it looks like I forgot to turn that into an exponent. Sorry about that. And so we're just left with c. So remember that the y-intercept is always going to be c. So why is that going to be useful? Well, let's take a look. So here's an equation that they're asking you to graph. X squared plus 4x minus 3 equals f of x. Okay, so the first order of business is to figure out what our vertex is. So using the negative b over 2a, we're going to plug that in. So negative b over 2a, a is 1. We end up getting negative 2. Now, yes, you can take negative 2 and plug it in here and evaluate that if you prefer. I'm going to use this formula because I feel like most of you have never used that before, so I want you to see how that works. So y is it going to equal to c minus b squared over 4a. Excuse me. So when we simplify this, this is going to be 16 over 4. So negative 3 minus 16 over 4, which you could probably do all this in your head. It gets you negative 7. Okay, so what that tells us is that our vertex is negative 2, negative 7. Negative 2, negative 7. 1, 2, 3, 4, 5, 6, 7. Right there. Okay. Awesome. Now remember that this right here, x equals negative 2, is your axis of symmetry. So we're going to put that in. Here's our axis of symmetry. Okay. And we're going to use the axis of symmetry and the y-intercept to help us graph this thing. So if the y-intercept is -3, I'm going to take my little point thing again, and y-intercept 1, 2, 3 is right there. We know that the distance between the axis of symmetry and this point is going to be the same as the axis of symmetry to the other point on the other side. So that means that there is another point right here. I didn't have to calculate anything. I didn't have to plug in values and figure out what it is. I just knew by the properties of symmetry that it's going to be there. And so now what I can do, I'll take the thinner line. This is going to look really funny, sorry. You're going to do a much better job than I am, but you can make your branches of your parabola now. Ooh, oh, I missed it. Ah! Oh gosh, that was terrible. Okay, yours is going to look so much better than mine. But you get the idea, right? Hopefully, yes? All right, let's try another one. Oh, we're not going to try another one yet. We're going to talk about this. Sorry. All right, so if we have, once again, our standard form of our quadratic, you have two options here. Your parabola is either going to open up, be a nice smiley face, or it's going to open down and be a sad face. And the difference between the two you'll be able to recognize is when A, this number here, is either positive or negative. So if A is positive, we're happy, and it opens up. If A is negative, we're sad, and it opens down. But what's more interesting is the fact that one of these has a minimum value and one of them has a maximum value. So the minimum and maximum are always found at the vertex. So because this one is opening up, it has a minimum value all the way down there. And this one has a maximum because it's opening down. So the maximum has a vertex all the way up there. And when we talk about the minimum and maximum values, we're actually talking about the y value of the vertex. Okay, so this is going to come in handy when you start doing some word problems. Yes, they are coming. Okay, here's the other example that I was thinking of. All right, so let's just go through the process again of figuring out what our vertex is. Plugging -b and 2a, figure out what that is. It's -1. And then whether you want to plug in -1 here, maybe that's easier because it's just -1, or using our new formula, whichever one you prefer, gets you the vertex of -1, 11. So let's see here. -1 up 11, 1, 2, 3, 4, 5, 11, right up there. Okay, so we know that our axis of symmetry is going to go through this. Now maybe you don't need to draw it in, maybe you want to draw it in, it's up to you. But we can see here that our intercept, our y-intercept is 6. So let's go 1, 2, 3, 4, 5, 6. And oh wow, that's really close, right? So that means that the other point is going to be right over here, knowing that our axis of symmetry goes through our vertex right here. Okay, so this looks like it's a really narrow, compressed, if you will, or stretched, if you remember from our first unit, parabola, and you can really tell that it's opening down, but we knew that already because of the -5. Okay, so once again, here we go. Wish me luck. Okay, that side, I seem to be able to do that side, no problem. Let's see how this one works out. Ooh, it's always worse. Okay, there we go. You guys will do much better, I'm confident. Okay, so you can see how easy it is to be able to graph these things. Okay, moving on. We've got more to do. Okay, domain and range. I think this is the last thing that we need to talk about. When you look at these parabolas, your domain is always going to be the real numbers. All real numbers. There's nothing that we can leave out. So that's good to know. But the range is going to be different for each situation. So if the parabola is going to open up, the range is going to start at the y value of the vertex, and it goes all the way up to positive infinity because it's opening up. So here's an example. Here's a parabola that opens up. We can see our vertex here is at 0, 2. That means that our domain is going to start at 2. I'm sorry, our range is going to start at 2 and move all the way up to the positive infinity. Remember, domain is all real numbers, so whatever. So if we wanted to write our range in interval notation, hopefully you guys remember interval notation. If not, go back and review that. So we have 2 with the hard bracket because we get to include 2 as a value. It is a y value. And goes up to infinity with the soft bracket or the parentheses because infinity. You can't ever find an end value of infinity. Okay, so that means that if the parabola opens down, then our range, and this is going to be what's weird, you're going to start at negative infinity and go up to the y value of the vertex. And this is where you probably are going to have some trouble. But think about it this way. Here's our parabola. Hopefully we can read off our vertex here at 1, 4. But you always start with the smaller number on the left-hand side. And the smallest number is going to be this negative infinity down here. And you would go all the way up until you get to this 4, and that's the highest number. So the range for this one is going to be negative infinity to positive 4. Okay, that's it for the introduction to quadratic functions. Hope that was all right for you.